We're Team Buff Bunny from Australia.
Hey, my name is Riley and I'm in charge of coding the interactive features for the robot.
Hi, I'm Taryn and I'm the artist of the team, so I'm in charge of the costumes, which I sew for the robots, and then I'm also in charge of the technical description poster and the backdrop.
Hi, my name is Kerry and I'm a programmer for our group who worked on the calibration feature for our main robot. I also worked on the mechanical construction of our main robot.
Hi, my name is Emma Burton and I help build the main robot and also some coding aspects, in particular with the gyro sensor-based system.
Hi, I'm Ben. I've been part of the physical creation of the robot as well as a little bit of the coding for the backup dancers.
We're coding in the programming language Small Basic with EV3 extension. Small Basic is a simplified version of the programming language BASIC, and it's meant to help students transition from block-based coding to text-based coding. Our bill of materials can be found in the following QR code. Let's take a look at the building process of our main robot and the backup robots.
Our backup robots are designed to act like moving platforms with an additional motor to enable hopping movements of the carrots.
Our main robot features a detailed sketch and a custom bunny costume, adding to its unique appearance.
The head includes complex gears, providing significant power to lift the heavy head costume and enables difficult movements. It was, however, challenging to come up with this gear ratio and gear mechanism, and thus we conducted many trials and tests to ensure that it would work as best as possible. Next, the arms powered by gears and gear ratios ensured smooth and precise movements, which was crucial for expressive gestures during the performance.
We have added knee and hip joints to the legs so that the leg movements can mimic those of a human.
The structured frame made of wood forms the robot's body, offering a solid foundation for all components and ensures durability.
Next up is explaining our 4 features. So feature 1 is our calibrations.
Calibrating our motors is essential to prevent damage during performances, as we have learnt last year. We rotate each motor to its limit, set the count to 0, then rotate it in the opposite direction to record its full range. We convert this range to a percentage, adjusting so that 0 is the motor's rest position, and ensure that each motor returns to this point after calibration. For detecting the stage boundaries, we use EV3 color sensors to return RGB values. By updating the largest and smallest raw values detected, we can calculate the range between these values as a percentage. These normalized values are used in place of the raw values, which prevents the interference of different lighting conditions on the colors detected by the sensors.
Our robot has been designed to be interactive with this environment, allowing for part of the robot's routine to be decided by the judges during the performance in real time. This is done in 2 ways. Judges can select the dance move for Buffy. How this works is that through the instructions on the backdrop, the judges communicate to us what their choice of dance move is. Then, based on their choices, we show Buffy a card. The color sensor on the torso of Buffy allows for a wide field of detection and identifies whether the color shown to it is white, green, or red. From here, the color sensor can communicate the color to the central control brick, which can use Bluetooth communication to transmit signals and information to all the other bricks, ensuring that all motors are in sync with the music and each other. At the end of our performance, when Buffy senses us or we wave at her, this is detected via an ultrasonic sensor. Then she responds with a high five. Both of these features allow for Buffy to respond to her environment during the performance, rather than predetermined movements.
Our robot's base is a multi-directional rolling platform built with 4 omni wheels positioned 90 degrees from each other. This feature has enabled an agile and precise multi-directional movement. In our second trial, we used 4 motors for better stability, but this only allowed 2 directional movements, forwards and backwards, left and right, as shown in the diagram. We needed a better solution, so we opted to put them in this position as shown. And to code this, we used a mechanism-kinetic wheel theory to improve our calibration and ensuring that the robot will always move in a desired speed despite its heavy weight, allowing shifting.
We wanted our song to be 120 beats per minute, so there would be a beat every half second. However, I wanted Dance to Somebody is actually 119 beats per minute, so we just sped it up slightly to adjust it and make it 120 beats per minute, which improved the timing during the verse.
Our timing algorithms move the robot every 4 seconds, matching the BPM for synchronized dance moves. Adjustments to 120 BPM improved the timing during the verse.
Bluetooth starts all the robots simultaneously to minimize errors. This coordination is key for flawless performance.
To sum it all up, we have incorporated a theme, costumes, and choreography to add to the cuteness and engagement of our performance.
Initially wanted to have a K-pop theme, we realized quickly that an animal would be a much easier costume than a human for our robot. We still kept the K-pop dancing as inspiration though, making the bunny dance at a disco instead of being on a world tour. The bunny theme all comes together when you look at the main robot bunny, the backup carrots, and the cute aesthetics of our TDP, TDB, and backdrop.
Custom costumes were designed to enhance the robot's character and appeal. Additionally, we have embraced sustainable practices by using second-hand equipment for our entire setup. We hope you enjoyed our presentation. Buffy, do you have anything to add?
Thanks for watching!